It really is. You keep looking at these failure cases and you realize that things fail all the time. So it is 8 o'clock. We'll get started. Hopefully the stream will work at least slightly well. I haven't gone and really watched the YouTube videos. I'm assuming those are fine, right? So the stream isn't perfect, but I think that's more a matter of the Wi-Fi more than anything else. Because I've streamed from home as well, and those streams seem to be just fine. But maybe I should just be sitting at home and I'll just not come in at all. Yeah, it's good to see you. It's actually hard teaching when you don't have faces to look at and get feedback. Because just even looking at you and you know, when people are like, their eyes start glazing over, you know that you're losing them. And that's useful feedback. Where if you don't have that, you know me, I can wander on and on. You guys have no idea what I'm talking about. I know, I don't wander. All right, so I'm going to jump right in. I did actually release grades, and on the next time I do a logistics slide, I'll note that I released the Project 3 grades for the people who were on time. And the grading is anonymous, so if you actually ask for a regrade, we have to re-import the grades because I don't know who you are from Gradescope. I did that because I don't want people to know who you are when they're grading. I didn't actually grade the projects there. That's just to try and keep it, to minimize the possibility of bias. Don't put your names in things, and it really will be anonymous. One of my favorite questions to give people when they're doing research projects, they're starting on research, is to ask them how they're going to control for bias in their research. And most people don't even know that that's an issue. Usually when you start looking at the evidence, you look at the data, what you see in the data is what you expect to see. Confirmation bias. Another problem that we run into a lot is survivorship bias. So we tend to think the people who got lucky did something to deserve it. And we all fall into that trap. All right, so I basically said, yesterday I'm sitting there going, this is just, I'm watching the questions and the discussion, and I'm going, this is just a little too confusing, and why the heck did they decide they have to change all the terminology again? So I'm going to walk through the PMMC paper and try to talk about the terminology they use there. I think that I understand why they changed that terminology, and it was, of course, to make this more complicated than it needed to be. Look, it's really simple. We use state machines. Why do we use state machines? Because we know that if we use a finite deterministic state machine, when we feed it a set of inputs, and then tomorrow we feed it a set of inputs, we get exactly the same output. I mean, I didn't teach that in here. I'm hoping that you guys were taught that somewhere along the way before you got here. That's pretty basic stuff. Okay. But we throw a little curveball in here, and that is we want to have these replicated state machines in an environment where we send you stuff out of order. You're like, what? Okay, so now this is a slightly different problem, isn't it? We're going to take that replicated state machine, we're going to give you a set of inputs in different orders, and we want you to come out with the same output. I started the course talking about this. I talked about how do we get consistent cuts. I talked about isomorphisms. I said, look, and it's really easy to see when the decisions we're making are not coupled. If you're doing a put on one key and you're doing a put on another key, and you're not dependent on the values of each other's keys, there's no coupling, and the order we do them in doesn't matter. So there's a whole bunch of these isomorphic orderings of events, and it doesn't matter. If they're isomorphic and we feed it to our replicated state machine, it will come up with the same conclusion at the end. So we've gone from it's easy to take one input and feed it in, and then to say if I take two different inputs and I feed it in and I get the same output, they're isomorphic. And the reason we want that isomorphism model is because the moment we put that network in there, it screws with us because it changes the order in which our inputs arrive. Okay, well, that's fine. So how do we make sure that we only ever end up with isomorphic inputs? That's all consensus protocols are about. Making sure that we all end up agreeing to an ordering of events that's isomorphic. Doesn't have to be identical. That's why your log and your log can be different. The consensus protocols, every one of them that we've talked about, is about making sure that even if the order of events in your logs is different, the actual outcomes are the same. I remember like an age ago, like Tuesday, I mentioned garbage collection. Why do we need garbage collection? It's a software engineering problem, actually not an algorithm problem. We don't need garbage collection. Ever worked with a Turing machine? You know what the Turing machine model is? A Turing machine model is a state machine, a finite state machine, and a piece of storage. How big is the storage? Why? Exactly. We do it because it's easier to reason about. That way we don't have to worry about things like garbage collection. So the very first thing to do is to say, I'm not going to worry about garbage collection. But PMMC talks about garbage collection, doesn't it? Because these people are not looking at this from a theoretical perspective. They're looking at it from the practical engineering perspective. And there's a certain sense to that, right? Because we've already got FLP telling us, you can't do that. Neener, neener. So what you're trying to do is impossible anyway. And us being much more practical than that, we say, well, but we can get close. And in all fairness, even when you start doing Turing machine analysis and you talk about complexity, anybody remember big O complexity? P, NP, polynomial time bounds, non-polynomial time bounds, those things that your eyes start glazing over. What? We know these problems are hard, and yet we still try to solve them. Traveling salesman. Scheduling. We're in systems. Anybody remember scheduling? Hard problem. It's actually a known non-polynomial bound problem. We know it's NP. Priority scheduling. Can't come up with a perfect solution. And yet, we still have operating systems that do scheduling. Because we have an approximation. Because we do it so it's good enough, and we make the choices necessary for us to be able to come up with something that's at least usable, even if it's not perfect. Do not let the perfect be the enemy of the good enough. And PMMC is much more on the good enough side, but it starts talking about a lot of stuff that you don't actually have to worry about when you're trying to design your protocol. When you build your software, you'll have to worry about garbage collection because you don't have an infinite tape. Do you remember Corfu? I'm actually glad that I taught the Corfu paper. I know I didn't go through it in great detail, but what Corfu basically built was the implementation of what appears to be an infinitely long log, with the actual pragmatic perspective of, but we're going to do garbage collection under the covers by deleting stuff that we don't need anymore. Corfu gave us a very nice, clean way of doing a replicated log that we can pretend is infinitely long. And why do we want a log in the first place? Because a log defines our inputs to our state machine. Okay, so I talked about the time differential version of the state machine. I take yesterday's input, I put it into the state machine, started the same place, put the same input in, get the same output. It doesn't have to be time separated. We could have two copies of the state machine. So I have copy A, let's see, actually I think it's row 1 and row 2, but whatever. I have copy A and copy B. And I put the inputs into those two state machines. At the same exact time, what do I want to have coming out? What do I expect to have come out? They're identical state machines. They're just copies. Hence the term replica. So when PMMC talks about replicas, they are talking about the state machine. When we turn this into something practical, which is in Project 4, our key value store, that's our state machine. That's our replica. So in PMMC, when they are saying state machine, they're actually talking about our database. One way of thinking of this is that that's our data. That becomes our data plane. That's the stuff we actually mutate because that's the thing we actually care about. And then there's the other side of this, which is we need to have some way of agreeing on what the order of these events are. Even though we're all sticking them in the log in different places and in different orders, we have to figure out some way of making sure that we end up with isomorphic orderings. It doesn't have to actually be exactly the same input. It just has to have the same effect. And that's the hard part to wrap your head around. Lamport's a mathematician. Lamport's papers provide a rigorous formalism so that he can prove that this protocol works. Liskov was a software engineering person. The PMMC folks, whatever their names were, are software engineering people. I mean, Osterhout and Ungaro are systems people. They build systems. Osterhout's been building systems for a very long time. His students built the very first log structured file system. He built his own operating system in the 80s called Sprite. There was a lot of interesting research that came out of that work, but he built real systems. So he's much more on the software engineering side of things as well. And so what does Raft talk about? Raft focuses on the log. How do we select our log across these things? Lamport gets to be the mathematician. He gets to step back and say, we're going to have priests. And we're going to have ledgers with our priests. And we're going to make notations in the front of our ledger and the back of our ledger, and we're only going to and we're going to move things forward based upon what the decision is. So he's trying to provide a very abstract model that he can then turn into a formalism to explain why these protocols work. Every single one of these people is implementing the exact same fundamental protocol. They just emphasize different aspects of it because they're coming at it from different perspectives. Why do the software engineering people focus on the log? Liskov doesn't really focus on the log. But she does focus on the leader election, and she is picking up Gifford's work on quorum replication. She wants us to be able to reason about what was the outcome of that operation. The view server change of Liskov and Oki is a leader election. So we have a data plane and we have a control plane. Our control plane is how do we decide what the order of events were. To solve that problem, no matter how we end up doing this, how we argue about it or discuss it, in the end, all we're doing is implementing a two-phase commit protocol. It's really it. We have a coordinator that tells us what the outcome was. It's amazing very useful for me actually because I've never thought of it quite this way. But reading these papers and listening to people and seeing the questions that people are asking, it's like it's all the same stuff. We just keep teaching it from different directions. That's to confuse you. I think it did the job. All right, so we're doing state machine replication. The simple model of state machine replication, and it's actually useful because PMMC does cite to this, is Lamport's replicated state machine model from 1978, which is older than almost everyone in this room. I'd be the exception. I wasn't that old in 78, but certainly not old enough to be reading Lamport's paper. I didn't have a computer yet. All right. All we are trying to do is agree on the order of operation. That's all we want to do. So we are independently sticking these things into our own logs and effectively deciding what we're going to actually apply from the things that we've received suggestions to apply. So in other words, we have proposals, and only some of those proposals actually get accepted. And the reason that we have that protocol is because we're only going to accept things that ultimately lead to an order of operations that gives us the same result. All the rest of this is just mechanism. That's all we're really trying to do. And I came up with this, actually it wasn't for this version of the class, it's for the other one. Somebody was asking about liveness in Paxos, and I was going, and they were like, well, you know, I heard you can do these things. I'm like, it's all a matter of degree. If you are actually trying to replicate your databases between, oh, I don't know, a database on Earth and one on Voyager 2, which is the farthest away human-made device of which I'm aware. Anybody ever heard of Voyager 2? That was launched about the time that Lamport published the replicated state machine paper. I think it was the late 70s. So it's out past the edge of the galaxy. It takes like 36 hours or something to communicate. I think it's 18 hours each direction or something. Crazy. Imagine trying to design your replication protocol so it can handle that kind of delay. How long does it take you to detect if somebody's dead? At least 36 hours, probably a lot longer. And I know that it shouldn't make any difference whether it's 30 nanoseconds or 36 hours, but somehow by stretching it out that way, it made it easier for me to think about that, to say, I got lots of time to deal with everything that could possibly be going on there. But it's the same problem. It does suggest to me a really interesting question, and that would be if you were going to design a data center that you were going to put on Mars, because now we're talking about maybe actually sending people to Mars. So of course, the first thing we need is to set up an Amazon data center on Mars. So you've been employed. That would be a really good question for a final exam. You've been employed by Amazon Web Services to design a data center that will run on Mars. Think about that one. Or we do it with a log. We really are going to do it with a log. Logs are very easy for us to understand because they are naturally linearized. And that's ultimately what we really want. We want a linearized set of inputs. And the reason I chose the very far away example is that let's make this very interesting. So we have 3 data centers, one on Earth, one on Mars, and one on Voyager. Voyager 2, which actually left after Voyager 1, but is now further out. Very odd. Oh, we get them out there slingshotting around the sun and stuff. It's lots of very interesting physics. Okay, so I don't know, Mars is what, about 20 minutes away, 15 minutes away, I don't know, and Voyager's 36 hours away. And it's the differential that I really like about it. That's why I picked those as examples, because it's almost plausible, almost. Can you see the problem here? Mars is actually closer to Voyager 1. We're actually closer to Mars than we are to Voyager 2. So the messages that I send from Earth and the messages that they send from your new data center on Mars get to Voyager potentially in the opposite order. So if we actually sent them at the same absolute time, your message would get there before my message. In fact, if I sent my message 19 minutes before yours, yours would still get there. So we don't have any clear ordering here. This doesn't even require that we have, fancy switches doing things like reordering the packets for us. No, it's just simply a matter of physics. It's a matter of the propagation time it takes for these messages to get across. So we can see why these are never going to happen in the right order. Okay, great. How do we get them to happen in the right order? Well, we're going to be retransmitting things, and that's going to give us some interesting behaviors. One of the things that happens in the Paxos protocol is that a request can be repeated. It can show up on multiple ballots, but we only want to accept one of them. So we have things appearing in different orders. We potentially have things that are requested multiple times. How are we going to get to this linearized order? That's all we're trying to do. It doesn't matter whether we're reading ViewStamp replication, Raft, Paxos, PMMC, even quorum replication in all fairness. All we're trying to do is end up with the same outcome. And we need our logs to reflect that. So we get a couple of puts. They'll show up in our log. These slides weren't great, but they were at least something that I could grab at 3 o'clock yesterday afternoon and say, I'm going to do this doc today. So could we use Paxos to do this? In Paxos, it's just two-phase commit. We send prepare messages, and then we send accepts, which are just in the two-phase protocol definition, that would be a commit. It's the leader that decides what the outcome was. It's the same thing that we did in two-phase commit, where we had a coordinator. The coordinator said, here's how this transaction ended up. So maybe you failed for a while, and then you came back, and you need to go and find out what actually happened. And we have protocols for dealing with that. That's great, not a problem. You remember Project 3? Do you remember you had to sync the backup with the primary when you added a new backup? The primary and the backup are the replicas. One of the things that is confusing about PMMC is they say, hey, we could add more replicas, and you don't even have to, they don't really care. It's very interesting. They don't actually care. It's like, that's not part of our problem. That's the control plane's problem. We're the data, that's the data plane's problem. We're the control plane. I thought that was kind of nice, realizing that as I'm wading back through PMMC, going, okay, it's good to point that out. We can add replicas, and they don't even show up in the protocol. Not my problem. It is part of the configuration. No, it's not. I take it back. They actually say the configuration doesn't include the replicas. Really? So when we go back to Paxos Made Simple, he had learners. His learners are the replicas. So it's kind of weird. The databases learn about the outcome after it's been decided. And if you think about it, it's like, okay, fair enough. It's just two-phase commit. So one of the differences between our two-phase commit protocol and Paxos, though, is that in two-phase commit, we started out with a coordinator, and it just was appointed. We didn't really have much to do with that. In this case, what we'd like to do is we'd like to be able to select a coordinator dynamically. If you remember in Project 3, we gave you a view server. Here you go. Here's your decision maker, sort of, right? What did the view server do? It selected the leader. Now we're kind of, so in Project 3, we kind of mushed things together and it wasn't clean. Now we're in Project 4, we're trying to pull that out because we actually want a robust view server. We want be able to select a leader in a way that doesn't give us the possibility of a single point of failure. The moment you have a single point of failure in a distributed system, guess what? As soon as it fails, your distributed system is worthless. Whether you're a data center on Mars or you're right here on Earth. So we're going to try and very clearly distinguish between who the coordinator of the transaction is, the leader, and what the outcome of the transaction is. That's why I started to talk about sort of this idea that our data plane is actually separate from our control plane. Our consensus protocol is a control plane function. When a leader gets elected and they propose a value and they collect the votes and they get a quorum, then they say, okay, it's now accepted. They record it in their log, and then they tell everybody what the outcome was. Now, of course, there is this interesting case where the leader might have lost contact. And these are transient failures. These are not permanent failures. Permanent failures are where, I liked the way they said it in PMMC, the state machine achieves a state where it does not transition to any other state, no matter what the input is. That's what they consider to be failed. You're done. We've unplugged you. So the PMMC folks are concerned about making this efficient. Now we get the software engineering side of things, right? How could we reduce the number of messages that we have to actually send here? Lamport doesn't care how many messages flow around here. He doesn't care if we get duplicate messages. I had this conversation on Tuesday about, yeah, I suppose you could actually have a client broadcast to all of the potential leaders, but in this case, it's actually going to be all the replicas in the PMMC terminology. It's going to be all the replicas. And they actually say that, broadcast all the replicas. And then all the replicas sit there and they try to get one of the leaders to propose this thing and the acceptors to vote on it and then tell them what the outcome was. In the real world, I don't think I'd implement it that way. Okay, so I'm going to broadcast this to all the leaders and my Voyager 2 key value store is going to get this thing day after tomorrow, and it's going to start sending messages back. Boy, talk about confusing. Actually choose the leader that's closest to me. Or maybe I'll be a little paranoid and say, let me choose a couple that are close. All right, so we have replicas. Those are the learners of Lamport's Paxos Made Simple paper, which apparently didn't make it simple enough. Or maybe it made it too simple and someone came along and said, we've got to make it more complicated because otherwise people will actually be implementing this thing. The leaders in PMMC are the proposers of Paxos. So these are our priests. Our replicated state machines are the ledgers. The acceptors, are simpler acceptors than what we had in Paxos Made Simple, but they're doing the same thing. These are the voters. So we have politicians and we have voters. Like some sort of purist democratic kind of perspective, right? Where there's no money flowing from people into the leaders so that they ignore what the voters want. I know, no political commentary allowed, sorry. It's all I've been reading about in the news lately, right? Is the whole thing about the Chinese government donating money to some Trudeau foundation who's now agreed to send it back. And it's like, the optics aren't great. Because the most important thing in life is to avoid the appearance of impropriety. As long as no one notices it, I've always loved that saying because, of course, the initial implication is you don't even want to appear to be improper, let alone actually be improper, but the way it really works in the real world is as long as no one notices that you've been improper, it's okay. Don't get caught. It's a terrible lesson from a social perspective. Much easier to talk about than this stuff. All right, so again, this is where we get isomorphisms. We talked about this before. This is all about getting consistent cuts and the fact that we can actually process lots of these operations in different orders and end up with the same outcome. It's super easy to see this when they're completely decoupled. The problem is sometimes those couplings are not as easy to see as you might think because the coupling of the values is in the client. In other words, the client reads one key and writes another key based on the value of that one key. So now there is an implicit ordering that we don't fully see. We actually don't have to solve that particular problem. We only have to solve the problem of keeping our own database consistent, not theirs. This is why real-world transactional systems get fiendishly complicated. When you literally can have multiple different databases and a single application that is modifying those multiple different databases, and it has to do them in a consistent fashion. So then we repeat the whole thing all over again. We do a coordinator, and the coordinator makes a decision about the outcome, and we have sub-transactions. When you get into real-world transaction processing, you're like, wow, we've got nested transactions and long-running transactions and dealing with all of these potential rollbacks and failures. It's all exactly the same thing. It's just, why have one layer? It's like a cake, right? A one-layer cake's okay, but a two-layer cake is better. And in software, we really go to the extreme here because we layer our software like it's a German chocolate cake. Layer, frosting, layer, frosting, layer, frosting, and a cherry on the top. We only have to solve this problem at one layer. The order in which we process things in the log just simply has to be isomorphic. It doesn't have to be identical. And that's what the protocol is trying to guarantee. All the discussions about, okay, yes, right. So how we label things, some people said, oh, well, they're using strings. I don't know why they're using strings. And actually, the reason they started using strings was because you're creating tuples. And you can actually map the tuple to integers as well. It doesn't matter. They have these charts that show up in Paxos made moderately complex. I loved the title of the slide deck, which was Paxos made moderately complex made simple. And I'm not sure that it makes it simpler, but it's still worth walking through it. So PMMC introduces this idea of a scout and a commander. The scout and the commander are nothing more than subroutines of the leader. They talk about them as being spawned processes, and I'm like, okay, so we're in a discrete event simulator, so how am I going to implement a spawned process? Oh, I'm going to have a subroutine that I call and a timer that like pokes it periodically. There you go. Spawned process now. Done. I mean, I could even put it in a timer. And that's how a discrete event simulator works, is that it is essentially an ordered scheduling queue, time-ordered scheduling queue, that when we start a new task, it's just an event in the queue. And when the clock gets there, we pull that event out of the queue and we call whatever the method is, the function, piece of code that's attached to it. Okay, great. Doesn't matter. I mean, and that was what made me realize that one of the things that can be confusing as you're reading through this is this idea that processes are not what we think of as processes in an operating system. They are a unit of execution, I suppose, but they're in a single-threaded system, they're just coroutines. They're just, I've got a queue of things to do. I pull the next thing off the queue, I do it. Maybe one of the side effects of doing that is to put something else in the queue. That's how the timer worked. The timer propagates itself. Okay, so the leader has a subroutine that it says, I'm going to send this message, and then you're going to start watching for responses to it. And of course, that means we can do retransmission if we don't get responses back, and we can decide what to do when we get those responses back. Because the responses are going to, of course, insert additional events into our queue. We're going to process them, and then eventually our scout's going to terminate. Now, what is interesting is that it talks about starting multiple scouts and only paying attention to the last one. So the leader could be sending out lots of proposals, but the only one that ends up being important is the last one it sent. And when it gets a decision on that last one that it sent, it then looks at what happened to all the others. Are there any others that I also accepted in that time frame? And that's what I found interesting as I'm walking through PMMC and going, oh, all right, I totally get that. So everything before that either was accepted or wasn't accepted. And if it wasn't accepted, it's now dead space in my log. And if it was accepted, I know that it's in the right order all the way up to the last thing that the scout proposed, the last scout proposed. So it's kind of like, wow, I can batch up my commits here, can't I? Because I know that if this committed, that all of the things that had been decided before it have also committed. And I know I went through that formalism in Paxos, because he talks about that. And when we talked about Raft, Raft explicitly said that. I'm going to send you the previous thing and the next thing. And the moment you know that this thing has hardened, well, you know that everything that's previously accepted has all been hardened up to that point. It's all been accepted. And the commander is about the leader election. Is it the other way around? Well, and why did they change it and say accepted or adopted? Because adopted is what you do for proposals. I hate these people. Oh, good God. Why couldn't they say elected? Because I'm sitting there looking at this, I'm going, okay, I looked at the slide last night, and it seemed to make sense. And I'm like, I thought this, because that was exactly it. I'm like, okay. I'm going to take a deep breath. Because the next time I do this, you won't benefit from this. You're the guinea pigs, of course. But the next time I do this, I am going to do this in a different order. And I'm basically going to talk about how horrible the terminology is. Because ultimately, I liked view stamped replication best. I thought it was the easiest to understand. And they're all the same. All we do beyond that is just add some extra stuff to handle other particular interesting cases. So the important thing is to get to the understanding bit. We're going to elect a leader. Once we have a leader, the leader can propose mutations to our replicated state machine, i.e. entries that we're going to put in our logs, and we're going to have to decide those. What was interesting in PMMC, to me at least, is the client sends a request to the replicas. The replicas send the proposals to the leader. The leader then asks the acceptors to vote. The acceptors then vote for one of those proposals, hopefully. And we either get enough votes for the same proposal that we adopt it, or we end up with some sort of a split vote, and we just keep trying. We just try another proposal. So what I think of as I'm thinking about how this is going to appear in my log is that, okay, so let's suppose that it really is the case of weird long timeout delays, and I don't know when I get my quorum for a period of time. I am going to end up with a lot of dead weight in my log. I'm going to end up with a lot of proposals that weren't adopted. And if they weren't adopted, they're just garbage. And that's why we're going to need a garbage collector. So We have these acceptors. These are the voters. Initially, we haven't accepted anything. We haven't seen a ballot. A phase 1A. Again, why? Lord, it was just built to make this seem a lot harder than it is. Phase 1A comes in from leader 0, ballot number 1. So we've seen 0.1 because that's the ballot that was presented by leader 0 with sequence number 1, ballot number 1. And remember, we have an infinite number of ballots and we never reuse them. So a ballot was only used exactly once. And that was a requirement of Paxos, was that we had to shard up the ballot space because we had to be able to select ballots. And of course, appending unique value to a local Lamport clock gives us a unique ballot. That's why you make it a string, because you could get bored, 0 through 9. That kind of looks like a decimal number, but we could be much more interesting and make it like, I don't know, Greek letters. Don't care. And so now we have a ballot number and we say we haven't accepted anything, but I got your ballot. I'm going to vote for your ballot. Or I'm not going to vote for your ballot. So now we get a phase 1A with leader 0, ballot 0. Why they picked that number, but they did. And we're going to say, I'm sorry, I'm not willing to vote for your old crappy ballot. That was yesterday's election, or 5 nanoseconds ago. It doesn't make any difference. You don't want to put your leader on Voyager 2. It's probably going to get a lot of nopes 3 days from now instead of a day and a half from now. All right, so now our leader gets to make a proposal. Now he's actually going to say, okay, ballot 0.1, command 0, and then A, whatever A is, it's a mutation. Put some value to a key. Append some value to a key. Doesn't make any difference. And again, this is when you walk through this, I'm like, that made it really easy for me to see this is actually control plane, because I don't care what the command is. The replica cares what the command is, and we don't care what the command is. So we don't care what the value is, and they don't care what the consensus is. They just want to be told what should I apply. And together we work this so we can end up with a consistent model. All right, so okay, we saw ballot number 0.1. We said, yeah, we like that ballot. Then we were told, here's what that ballot corresponds to. It's like, here, do you want to vote for me or not? And this is what I'm going to do afterwards. I'm like, this does sound a lot like politics, doesn't it? Great. So now I've accepted that. And I say, I've accepted it. I don't have to do that. It is possible that the acceptor could have changed its mind, right? If we get one of those trailing ballots with a different proposal, we're going to refuse it. Ballot numbers only increase. Yes, question in the back. I think they're equivalent, actually. I think you could do it either way. I would probably just drop it because I don't really care. Sorry, I just received a letter from you from 1947. I didn't live here in 1947, so something addressed to occupant. I don't care about whatever. Yeah, I would just throw it away. But maybe you're really polite. Maybe in your protocol, it's actually much more important for you to say reject. I think you could make either one of those work. Okay, so here we go. We have accepted that state change. Ballot 0.1, command 0, command A, or sequence number 0, command A. Ballot numbers only increase. We only accept values from the current ballot. So we never accept values from old ballots, and we never remove ballots. Well, so much for garbage collection. In fact, the easiest way to start with this is to say, let's ignore garbage collection. We've got infinite tape, fine. And then eventually we'll go back and realize, well, we can actually put garbage collection in. And that's consistent with what I recommended from office hours, which was don't bother with garbage collection until you've got everything else working. Because frankly, that's the least interesting part of the problem. That's the software engineering bit. It'll be important when you're working for the Amazon Mars data center, because you're only going to have a small amount of memory there initially until you can get the nanobots to dig through the dirt and create more memory for you. If a value is chosen by a majority on a given ballot, then any value accepted by any acceptor in the same slot on that ballot has the same value. What does that mean? Well, that means no matter what the order was here, we're going to end up with the same outcome. So even if we end up with the same slot, different ballot, we're going to end up with the same value. That's that whole isomorphism thing. Oh yeah, okay. So there were some variations in the way that things arrived, and we processed them slightly differently, but it was the same exact outcome, and that's okay. And that's the invariant. So this is the invariant model, which says these are the things that we have to guarantee in order for our protocol to work right. Since the purpose of our protocol was to make sure that we ended up with the same output, that's what we care about. We don't actually care if there was some variation in the order in which things arrived and were agreed upon, as long as in the end, we got the same result. Okay, back to our little picture, election, proposals. So walk through the election. So we have a leader. There is no leader. This is the startup condition. So no one is leader. And of course, I love how we simplify these with pictures of one leader. But of course, it's not very interesting, is it? That's project 3, where, okay, but that's fine. So we don't have a leader. So you come up, and we don't have a leader. We need to elect a leader. So we walk through this, and we send out to all of the acceptors a proposal to elect me. Vote for me. I will solve all of your problems. And of course, the acceptors, being very reasonable, say, no, you won't. Acceptors don't have to vote for leaders. Now, that goes back to the question earlier, which is that an explicit or an implicit vote? I mean, the benefit of an explicit vote is that then the leader knows their ballot's dead. So you could potentially see where that might be useful in a real world situation, but leader can't actually be elected until they've heard from enough voters. So the leader, the voters can just simply go, I'm not voting. That's the abstention versus the no, I don't want you model. Or they could vote. They say, yes, we like you. We want you for our leader. Now notice that we had 3 acceptors, but only 2 voted. But that's enough for the leader to say, okay, I have now won. What that means, and this is present in PMMC, is that the leaders have to know how many acceptors there are. This is called the configuration. And if you go and you read the PMMC paper, anybody read that yet? It actually says that the configuration contains the list of leaders and acceptors, but not replicas. That was the one that kind of surprised me. I'm like, oh, we don't actually care about the database. Okay. We're doing all of this for database consistency, but these guys don't actually care. They really are like politicians. All right. Our leader is now active. This leader is now capable of proposing things. Now, honestly, This is nice and simple. We got one leader, we got 3 acceptors. This is perfect. But of course, this becomes much more interesting when we get multiple leaders, because then each of these leaders will be able to propose different changes. In Paxos, every priest was potentially a leader. Every priest was actually allowed to propose changes. When you look at Raft, this whole leadership protocol thing is a lot more interesting, because what they're trying to do is reduce the number of messages. If I have lots of leaders and we're all proposing the same things, what's going to happen is we're going to end up duking it out to try and figure out which of us is going to be the successful leader. And even last Tuesday, like a month ago or something, I commented on this. I said, this isn't very efficient, is it? So this is back to the software engineering perspective, which is we really don't want to send lots of unnecessary messages that are going to create confusion. So it's better for one leader to be making this proposal. And most of the time, that's enough. Why would I want to use multiple leaders proposing the exact same change? What does that give me that I don't get from having, just picking one of the leaders and saying, please propose this for me? If that one leader's failed, it's going to be faster. So this is a liveness problem now. If liveness is really important to me, I will probably end up choosing multiple leaders. My replicas will end up sending that request to multiple leaders to try and make sure that it happens quickly. But of course, that's not exactly obvious, since now we're going to be fighting about which of these ballots, which are all proposing exactly the same thing, we're going to select. Networking is cheap. And lots of messages, because we'll wait for 36 hours for the message to come back from our Voyager 2 data center. This is how physics actually affects computer science. It's all about relativity. So when should we try to select a leader? I already mentioned at the beginning of time. The other time that we do that is when we think the current leader has failed. Now, of course, one of the possibilities here is the current leader hasn't failed, but our connection to that leader has failed. We cannot distinguish the difference between these. And that is why we don't actually know if the leader is fail-stopped. Oh, look, somebody unplugged them. Or the network has partitioned us off. Oh, look, someone unplugged us. The paper itself actually describes a pinging algorithm, heartbeats. We see this in ViewSnap replication. We see this in Raft. We see it in PMMC. I don't think Paxos actually explicitly says that there's a pinging protocol going on, because Lamport's a mathematician. He's not interested in that. So he's going to let you, and it's perfectly acceptable, to call a leader election whenever you want. Except, remember, he let everybody be a leader. Every priest could propose ballots, and he was fine with that. That may be why systems people have a hard time wrapping their head around Paxos, because Lamport's writing it from the mathematician's perspective, and not from the I have to actually build this thing to make it work perspective. But sometimes the I have to build this to make it work people don't make it any simpler either. Witness PMMC. So the idea here then is that we're going to have some sort of back off too. So if we don't get elected, we're not going to immediately stand up for election again. We're going to wait for a little while, and that's pragmatic. When we looked at Raft, they talked about 150 milliseconds to 300 milliseconds. That's one of the reasons I liked the Voyager 2 data center, or even the Mars data center, because that means 150 milliseconds is completely unrealistic. That number is based upon how long do I think it's going to take to hear back? Your question. So the benefit of, I think you can confuse two things there. The benefit of having multiple leaders is that it can improve liveness. And if you were in a high failure environment, you might actually want to do that because it would improve your liveness. But in the real world, the failures are rare. And so this is where you try to design for the common case. Having a single leader means that most of the time what happens, and when you look at the raft animations, that's exactly what happens. One node is proposing changes, and then the changes propagate very quickly. And then another proposal comes in, it propagates very quickly. If you actually have, imagine, I don't know, we have like 15 people in this room. Imagine if everybody was trying to shout out the proposed change at the same exact time. No one would hear you. We'd have this cacophony. So we're going to put a little bit of delay in there, 150 to 300 milliseconds. And then somebody's going to be speaking up first, and we're probably, hopefully, that's enough time that ballot will win, and then it doesn't matter what the other people said. The interesting problem here is that as the time to communicate gets more and more staggered, the downside to having multiple leaders is you're never going to end up with a consensus because you're never going to get enough votes before somebody else proposes a higher numbered ballot. And then they're going to propose a higher numbered ballot, and then the people who haven't voted already are going to jump on that, and now we don't have a consensus there, and it's going to time out, and then everybody's going to start all over again and propose a new ballot. Because remember, what happens when we don't get enough votes on a ballot? It doesn't pass. It's not adopted. And so we time it out, and we're going to start a new ballot because we never reuse the ballot. So we propose a new ballot. And this is why those numbers that they put in those papers are based upon understanding what the characteristics of the specific network are. But we're sitting here in a discrete event simulator for this project. So we kind of have it pretty easy because we get to define all these things and reason about them that way. It would be really fun to put something that had a 17-hour or even 17-minute or 1-minute delay time. 1 second delay time. Imagine that your usual timer is 150 to 300 milliseconds, and something sitting on the other end of a satellite communications relay that takes 2 seconds to get back to you. Your model doesn't fit the real world. So your model, what you've just spent your time building, doesn't really work correctly. This is good for us because it means that when Amazon needs their Mars data center designed, we're all going to have, well, an opportunity for employment and maybe a trip to Mars. Probably not. That's probably going to be one of those data centers that no one actually is allowed into. Because that's the real disaster recovery data center. Marvin shows up. We have a solution, Marvin. We're going to put our data center on your planet, which you're not going to destroy. Back to our picture again. This time, let's look at the actual proposals. So the leader's handling the proposals now. The replica, so a client talks to the replica. The replica says, okay, I need to get some agreement on this, and it sends the request, the actual operation, to the leader. Now remember, if there's multiple leaders, we can send it to all of those leaders. And if we were doing multiple leaders because we wanted liveness, that's exactly what we would do, because it would kind of defeat the purpose of having lots of leaders. But maybe we want load balancing. I mean, there are other reasons. This is why there's no single implementation of Paxos that's going to work for all of these cases. And this is why people argue about all this stuff. Because when we get to real world implementations, there's a lot of different things we end up balancing back and forth against each other. This is why you could build 6 different Paxos implementations in your life, which is probably more than you'll want to. Each of them taking 5 years to get right. And they'd all be different, but it'd all be Paxos. All right, so now we have a proposal. Our proposal number 1 is Command A. And we're going to send this out to all the acceptors. We send to all the acceptors because in the voting protocol, we need them all to get this. So we can broadcast it, we can multicast it, we can unicast it repeatedly. Doesn't make any difference. We're going to send it to all the acceptors of which we know. That doesn't guarantee they're going to receive it. It doesn't guarantee they're going to receive it at the same time. So, of course, we're going to have our little retransmission timers going off. They're allowed to say no. I'm sorry. I'm not willing to vote for your crappy proposal. Try again. Or they could say, yeah, this is great. Now notice, we don't need to have all of them say no. So one of the reasons that you might want to have a voting protocol where they explicitly said no is because you know right away not to retransmit anymore. That is sort of an implicit kind of heartbeat or ping. My gosh, aren't there a lot of branches in this decision matrix of how to build this thing? This is why you can have an entire class over what is basically, for all intents and purposes, Paxos. Because we have to build all that requisite knowledge up and talking about quorums and logs and networks and whatnot, and then we all spend our time to get here. And once we get past this, then we're going to talk about all the cool things we can build with it. Once it's been accepted, then we tell the replicas what the outcome of that operation was. Now, this is the beauty of it. Remember, this is just two-phase commit now, right? Okay, everybody. Time to update your database. And there's a lot of hand waving going on in this slide, just to say, just because. But yeah, that's the basic idea. So that replica on Voyager 2 is going to be updated day after tomorrow. So in PMMC, they introduced this concept of a slot. I think of it, because that's the way these drawings are drawing, and it made sense once I actually saw the picture. I think of it as a position in the log. The slot is the position in the log. And our invariant is everybody accepts the same value in that slot. Even if it wasn't on the same ballot, which is the part that's a little bit of wrapping around of my head. But okay, so here we go. We've got our log. So we get a couple of puts in there. We've got our replica. Now, this is where it becomes interesting. This is our log. And this is the picture that really helped me. And the reason it helped me is because when I'm reading the text, I'm thinking slot in and slot out the way they were described. They describe slot in first, and then they describe slot out. So I think of slot in as the lower index and slot out as the higher index. And I was going, what? I bashed my head against the wall. And then I saw this picture and I said, oh. And it suddenly occurred to me, this is exactly what I implemented 30 years ago when I was building a log 30. When I was building a log, and I was about pretty much your age and had no real clue what I was doing. I was 24. I really didn't know what I was doing, but I ended up designing something that was exactly this. I had lots of parallel activity that was going into this thing, and I had this asynchronous window where I didn't know if things had actually been adopted or not, which in my case, adopted meant whether they'd been actually written to disk. Same exact thing, though. Same exact principle, which I thought was really cool when I finally looked at this picture and said, oh, okay, this makes sense. So effectively, I have a window of things that I don't know the outcome of yet. All right, that's cool. I can live with this. And eventually what's going to happen is I'm going to have to decide all of those things in that window. What was adopted, what wasn't adopted. Now, in my particular log, effectively everything that got written Once that window had been written out to disk, it was hardened and it was adopted. I didn't really have a model where I would reject things, because that's a much harder model. But that's the one we're implementing in Project 4. Okay, great. So this is what they mean by slot in and slot out. Slot out is the oldest undecided thing I know of, and slot in is the next entry in my log I haven't used yet. And this is where knowing that I have an infinitely long log is very helpful. It's an engineering problem to implement an infinitely long log in a finite amount of space. The way we do that is called garbage collection. How do I garbage collect it? I don't have an infinitely long tape, but I want to simulate one. And what I notice is that I don't actually need all that old space. I think the cleanest way of doing that is the way the Corfu folks did, which is, we'll just unmap everything that you don't need anymore and we'll recycle that space. So we logically have an infinitely long log, but physically, there's stuff in there you just don't need. So we'll just throw it out, recycle that space. Perfectly reasonable for building a real world solution. Not perfectly reasonable if you're trying to do a formal mathematical proof. So that's Lamport versus everybody else. The leader tells the replica that there has been a decision. And the replica now hardens that proposal. And moves its slot out forward. And now we know that that operation in that slot was committed. And we can this process, so on and so on and so forth. And we just keep moving our slot in and our slot out forward. So in the simplest of all worlds, we probably only have one entry that hasn't been confirmed in our log. That's the easiest to think about. When you start opening that window up and you go, well, I don't actually know what ends up happening to these things, that gets harder. Question? That's correct. So notice what he did. Well, we've already asked the leader to propose it. So the leader is off doing its thing, but there's been a conflict on that ballot. So the order of events is actually differed here. So all we care about is, and in this instance, notice these are independent keys. So all we care about here is what order do we need to apply them in. So yeah, we can move the entry in the slot. We're not reusing ballots. This is not the balloting protocol. This is now the log that we are using the whole balloting protocol over to decide the ordering of. We have no idea. This slide doesn't actually say anything about what's going on with there, that's the right button. It has no idea what's going on with that request, that proposal. So here we have we get a decision that says put K3 B3, because that's coming from a different replica. Somebody else has proposed a different change in parallel. So we get a notification that this has been decided. So now we have to put this into our log in that slot, and we say, yep. And then we get another one, and we repeat this process. Oh, that's ours. No, this is actually ours. Notice that this is K2V2. That's what we had proposed. So let me go back. Now I see it. K2V2, right? So we had already proposed K2V2. We sent it to the leader. But the leader said, sorry, somebody else snuck in and got theirs in before yours. So the log order is the other replica's proposal now takes that slot, but yours isn't gone, so you still preserve that because you've already asked for it. So either you're going to be retransmitting that because we had a leadership change, or the leader is off busy negotiating, doing its job, in which case then you get the acknowledgement of your proposal. But now we know the order in which the operations should be applied, and we end up with the right log. That's the interesting thing, right? The log here is the actual definitive list of the order of operations, and the point here is they're saying it doesn't matter what the order of the ballots was, everything that ends up in the slot is exactly the same regardless of the replica. So yes, the decision-making process is very sloppy and very, very fluid, but the log has to be very consistent. The log needs to be the same on every replica. That log on other replicas could still be behind mine, but the protocol will guarantee that eventually they will be able to catch up, assuming that the replica isn't dead. We're not asking you to do reconfiguration in Project 4. Essentially, that's what we do when we move to Project 5, is we're doing a sharded key value store, and we have to do reconfiguration of the key value store. So you shouldn't worry too much about reconfiguration in Project 4. You want to think about it, that's great. And even in the original Paxos paper, Lamport talks about the possibility that you could add additional acceptors and leaders. You'll notice that it doesn't talk about replicas. That would be another interesting challenge in Project 5, is that, of course, the whole point of a sharded key value store is adding replicas. So the replicas have to agree on who the leaders are. So this is where, when we do a reconfiguration, now all of a sudden these replicas have an active part in changing the configuration of the system. And that's why we have a whole protocol around that that's kind of independent. It's similar, but it's independent of the normal protocol. So reconfiguration events are typically rare. And this is actually a real world concern, which is, okay, I have a dead server. I have to really replace that dead server. So for example, when we have, you're running in an environment where you have Kerberos running, and Kerberos is a multi-server environment, multi-server setup, probably the most well-known of which is domain controllers. And you can actually add domain controllers, and you can take dead domain controllers out. And that's a reconfiguration event. And that's when you have, but this is the kind of thing you do once a year, not hourly. You bring a new data center online, you have to do a reconfiguration event. Yes. And you have to make those protocols work correctly. You can understand from an engineering perspective why this is challenging, is because you don't do it very often. And things you don't do very often are hard to test. But don't worry too much about it. It is in the paper. I left the slides in there because I said, okay, well, it's in the paper, and it's good to tell you that's not something you have to sweat for Project 4. And I'm going to stop at that point because I think this hopefully it achieved the goal, which was to wade back through the terminology and try to make things slightly less murky. Everybody's done with Project 4, right? Almost. Cool. I was originally going to do formal modeling because I was like, ooh, that would be fun if somebody wanted to pick up TLA Plus and write a formal description of their algorithm and prove that it works. Because there's always somebody who's got nothing to do in their final term at university, right? But we'll do that next Tuesday. It still is good to go through those tools, and now that you see how complicated this can get, you'll have a better appreciation of why it might actually be good to have a model that you can prove that works, so that at least This is the way I usually explain it. If you can't explain your model and you can't prove that your model works, it is unlikely your code will work. If you can explain your model and prove that your model works, you might have a shot at building code that actually works. There's no guarantee of that either. So, and I just left the questions in there because it was like, the reason that we end up with PMMC and the reason that we end up with Raft and the reason we end up with view-stamped replication is because the software engineering people want to make something that actually works in the real world. Lamport wants to prove that his protocol works correctly. So his is a mathematical model, and I think that's great. And it's really important to understand that this stuff does actually work. But what makes building actual Paxos systems really hard is there are ugly, ugly error cases. It's all the edge conditions that will kill you. And there's a lot of edge conditions here. And normally when you're writing an app, you write some GUI application and you're like, I don't care about those. Just let the application die and I'll restart it. Here, it's like, let's just scramble your database for you. What's wrong with that? Yeah, except you won't like that when your bank does that to your bank account. All right, see you on Thursday. Tuesday. Today is Thursday. See, I don't even know what day it is anymore. See you on Tuesday. Or it warped from the future, I don't know which. It's mostly just sleep deprivation. Hopefully the stream works. Hold on.